Hello and welcome to the next lecture of the module Decision Making for Autonomous Robots here at the University of Bonn. My name is Marija, and in this lecture we focus on search-based methods for robot motion planning. If we have a discrete, graph-like representation of an environment, how can we get the robot to travel through it safely, to reach a goal and perform a useful task there? We start by reviewing the planning problem and the foundations of search-based methods, and then we move on to discuss different algorithms for uninformed and informed search and their various aspects. So to start, let's review some of the content from the introductory lecture to robot planning. In the planning problem, our objective was to find a sequence of valid configurations connecting the robot from a start configuration to a goal configuration, its environment, without running into any obstacles. Specifically, we looked at the classical path planning problem, which seeks to find the shortest possible geometric path connecting the start to the goal. And as we said, the closer a given path is to the shortest possible one, the better or the more optimal it is. We then looked at different methods shown here for solving the robotic planning problem in practice. We discussed examples for each of these methods, their properties, advantages, and disadvantages. Specifically in this lecture, we focus on search-based strategies here, which use discretized representation of the robot environment. These strategies are not only useful in robotics, but also in any other combinatorial optimization problem, for example, solving a puzzle. In robotics, we can also combine them with some of the different strategies here. For example, we can use a geometric analysis of the robot workspace in order to create a graph or roadmap of where it can move. And then we can use a search-based algorithm in order to find the shortest possible path from a start to the goal. So to apply a search-based algorithm, we need a discrete representation of the environment, and we look at some examples on the next slides. We need a model of the robot, including its dynamics, its kinematics, and its geometry. And of course, we need to specify the start and the goal configurations, defining what we want the robot to do or where we want it to move. It's important to note that when we solve the planning problem here, we will exclude possible sources of uncertainty, including the actuation uncertainty and the sensing uncertainty. This is in contrast to our previous material on decision making, where we had an explicit model of the robot action uncertainty, and then we used this in order to generate the probabilistic expected rewards when the robot takes particular actions in a sequence or decisions. Over here, in line with the discrete nature of the problem, we'll be assuming that the robot can move perfectly when we generate a path for it. So how can we characterize a search-based method in this formulation? So all a search-based strategy does is try to explore the environment systematically under a set of given rules. Each algorithm that is search-based uses different rules in order to explore the space starting from the start as it branches out, and we'll look at how this actually influences its properties and the paths that it can provide us in practice. So the goal now is to go on a deeper level of abstraction and try to really understand how these algorithms work and what steps we need to take in order to implement them. So let's talk in more detail about the environment. So as we said, we need a discrete representation. This allows us to capture the continuous nature of the problem in a compact way. And a discrete form that is often seen in planning is a graph. A graph is just a roadmap of where the robot can move. It has vertices corresponding to collision-free configurations for the robot, and edges, which are collision-free paths connecting vertices together. So this is where the robot can travel. A special case of graphs that we often encounter is the grid. A grid is a uniform discretization of the environment. And we can specify a resolution and impose a particular grid over the environment where each cell of the grid corresponds to a robot configuration. And we can say that each cell is either containing an obstacle or obstacle-free. So in this case, the cells would correspond to vertices. And to get the edges, we can simply look at the adjacencies between the cells, so how the robot can travel from one cell or one configuration to another. This can be done, for example, using 4-neighbor connectivity, in which we say the robot can travel to the top, bottom, left, or right, or using 8-neighbor connectivity, where the robot can also travel diagonally. There are other angles and other methods of defining the edges, as well as the actual nature of the grid. For example, though we look at square grids here, we can also consider, for example, hexagons. There is nothing restricting us to this particular shape. Another data structure which will also be useful is a tree. A tree is simply a minimally connected graph that has no loops and is fully connected. And this data structure, as we will see, will be valuable when we consider that search-based methods effectively expand and branch out starting from the start as they search towards the goal. So let's make this more concrete and look at a real robot. So over here we see a robot called Shaky from the late 60s, which was a real pioneer of planning and artificial intelligence. Shaky is a ground robot with wheels that is here in a room with several different obstacles. And of course, when planning, we can specify any steering constraints as well as its shape. Now, if we want to apply a search-based strategy and take Shaky from one end of the room to another, for example, here are some of the discrete representations that we might consider. So on the top, we see a graph that has loops where the circles correspond to vertices that are numbered and the lines correspond to edges. Similarly, here we have a tree, which is simply, as we said, a graph with no loops. And over here we see a grid representation that has a uniform resolution with square cells. And we can just color in which cells are containing obstacles, depending obviously on what the environment looks like. Now, it's important to note here that in the case of graphs, for example, when we apply search-based algorithms, they don't really understand how the environment looks. This is all the information that we need that is very concise, that allows us to find the most effective paths. So that's a 2D example, but what if we move away from the 2D world on ground robots and into a 3D space where we can actually also fly, for example, with the UAV? So here we see a small UAV that's in a room with also some obstacles, and it has 6 degrees of freedom, it has an altitude, and it can also move along the plane. So in this case, one possible strategy for discretization is to consider a 3D volumetric map, such as the popular octomap shown here. So here, rather than flat cells, we have 3D voxels, and each corresponds to a particular location in 3D, being as obstacle and obstacle free, and we can model this in a probabilistic way as the robot is mapping. And so this is one possible way of discretizing the environment. However, it's easy to see that if we apply a search-based strategy and try to search this very dense representation with a set of rules, we quickly run into computational issues. So perhaps a standard search-based strategy, such as the one discussed here, would not be the first choice. But this is one method of actually discretizing the continuous space, such as this, as we did in the 2D example. And of course, in both 2D and 3D, we want to cater for the fact that we need to set the resolution of our grid or our map to an appropriate level so that we can actually capture the structure of the environment. So for example, if we have a narrow passageway that the robot can just squeeze through, we need to make sure that the resolution of our grid for path planning is such that it actually does not obstruct the space, but rather captures the free space as well. These are just some considerations to take into account, especially moving on to the 3D world, to make you aware that we need to consider more efficient methods. So now that we understand what search-based algorithms are all about and the problem setup, how can we compare different algorithms or different rules for exploring the search space? What kind of criteria and what kind of metrics can we use? Well, here we can talk firstly about completeness. So does our algorithm actually find a solution? And if it doesn't, if there is no solution, can our algorithm report that? Especially relevant for grid-based representations is the concept of resolution completeness. This is where we say if the underlying grid is fine enough, then the algorithm can find a solution. Another concept is optimality. Can our algorithm deliver the best possible solution given a specific objective? So in classical path planning, does our algorithm give us the shortest possible path from the start to the goal, or does it just give us a path which may not be optimal? We also need to ask ourselves, do we need the best path, or do we just need a solution? And then we also need to be aware to measure the time and space complexity of different algorithms. So we can measure, for example, the runtime of an algorithm. Does it take 1 second, 5 seconds, 10 seconds, or more or less to find the solution? But another way and a more principled way of doing this is looking at its complexity. So subject to an arbitrary input, can we bound asymptotically the worst case performance of an algorithm? And this is not something that we go into too much detail here, but it's important to be aware that this is actually a good measure for assessing how computationally efficient an algorithm is. And in terms of space, how much memory do we need to perform the search? What kind of variables that we need to store? So what would be our general approach now that we have a discretized representation of the space, we have fully specified our problem, and we're aware of the different criteria we can use to evaluate our algorithms? What's our general approach? So essentially we start with an initial state, initial configuration, or an initial node in graph terminology, and then we expand that state by generating its successors. So we keep branching out from that initial state, and the next state, the next node that we pick to expand will depend on these rules that we'll define later for different algorithms. So we successively look through the nodes of the graph, we explore. And then we stop either when we find the goal state, so we have solved our problem, or we have considered all possible states, so we have fully explored our graph. In this case, there is no solution. Here's a visualization of the concepts of generation and expansion in reference to nodes or states. So when we expand the parent of a node, we generate it. So that node is like at the leaf or the frontier of our search tree. Let's say if we're starting from the start and we're branching out, the nodes that were most recently generated would be the last ones, or the ones on the frontier. And when we expand our node, that simply means that we generate its children. So we go a step deeper, a step further into the tree. And these are two key concepts and steps that we need to understand in search-based algorithm searching. Here are some more definitions that will be useful. So a parent node is intuitively just the node that generated its children. So the previous node that was the leaf before we got to the new leaf. So which node do we need to expand in order to get a newly generated node? So obviously here is the light blue one and the dark blue ones are its children. And this terminology is there because parents obviously came before the children, so this happened earlier, at an earlier step of the algorithm at a point in time. And then we have the idea of an open list. An open list is a collection of nodes that are neighbors of expanded nodes, so the nodes that are generated. So these are effectively the children of the expanded nodes and the possible candidates for the next expansion. So what we do in search-based algorithms is we look at the open list and we pick, using rule, one of the nodes to expand. And then we also have the closed list, which is all the inner nodes of the tree, the nodes that were already expanded, and therefore it's not interesting for us to consider them again because that's what we already searched. So we consider two different types of search algorithms in this lecture. The first is uninformed search. This is simply when we only have the problem definition available when we apply our rules for expansion. So we don't use any additional information or so-called heuristics in order to guide our search. We just do the search blindly and brutally in a very brute force way until we find the solution. And some examples of this, which we look at next, are the breadth first, depth first searches, uniform cost search, and also Dijkstra's algorithm. So these algorithms do not use any further information about the problem beyond what is already explored in the graph. An alternative way of searching is using an informed search strategy. An informed strategy uses more information in order to guide the search. And the reason why one would want to do this is to make the search more efficient. So in some way, we're injecting more knowledge into our search problem in order to find the solution quicker, or trying to do this. So when we look at the nodes that are currently on our open list, we have the capability to say that one node from this list appears more promising than the other based on a particular heuristic or a particular intuition. And we'll look at different ways of formulating this mathematically further on in the lecture. Some examples of informed search strategy are the greedy best first strategy, A-Star, which is a very popular search algorithm for path planning, and also Dijkstra and Dijkstra Lite, which are especially designed for dynamic environments. With those preliminaries in place, let's move on to discuss uninformed search strategies. So now let's delve into the details of first uninformed search strategies, which search for the shortest possible path in an uninformed way without using any knowledge of the problem domain and in a brute force manner. The first algorithm that we look at in this category is called breadth-first search. And the basic idea here is simple. So if we start from an initial node or the robot initial configuration, we want to generate all the nodes on a particular level of depth first in the search tree before looking further. So effectively, we're going layer-wise, starting from the initial node. Here's an example where the blue arrows show the order of the expansion. So if this is our root node, our initial node at level 0, we go to all nodes of level 1 first before going to all the nodes of level 2. It's easy to see that this algorithm is complete. So if there is a solution, it will find one if we give it enough running time. If the edge costs here are equal and non-negative, then the solution is also optimal, because we're always closest to the root node when we find a solution. In the worst case, in terms of complexity, the breadth-first search needs to look through all the nodes and also all the edges of the graph. So we can formulate the complexity in this way. But for larger problems and larger graphs, it's more useful to formulate it by looking at the so-called branching factor, which is the average number of nodes that a particular node in the graph branches out to, so the out degree, as well as the distance from the start node. And in this case, we can formulate it as such. Another algorithm that we consider that is opposite of breadth-first search is depth-first search. So here we look as deep as possible down into a search tree before backtracking and going down another branch lower. So if the algorithm doesn't find a solution and it reaches the bottom of the graph, it will go back and look down another branch. And this is shown here again in the blue arrows, where we go down on the left first and then moving towards the right as low as possible. One disadvantage with this approach is that it's not complete. So actually, if our graph is infinite, the algorithm may get stuck before it gets the chance to find a solution that might be in other parts of the graph. So along similar lines, the algorithm is also not optimal. Because it goes as deep as possible, it might not get the chance to explore shorter and more optimal solutions. So here's a visual comparison and animation of breadth-first and depth-first search. So in the case of the depth-first search, we're always going down, searching along the depth, whereas in breadth-first search, we go layer-wise, searching along the breadth. And which one is better to use? Well, this highly depends on the structure of our problem. For example, if the optimal solution is over here relatively early on, then depth-first search will find it very quickly. But unfortunately, due to the order of its expansion, it may also get stuck in an infinite depth here or not be able to find the optimal solution. So those are some algorithms that work when the edge costs are equal and constant. But what if they're different? For example, what if we generated a graph of the environment and one edge connecting two vertices, two nodes or collision-free configurations can be, for example, 1 meter or 10 meters. So what if they're inequalities? Here we can use a uniform cost search algorithm. So here what we want to do is always expand the node that has the lowest accumulated cost. So what is accumulated cost? It's an important concept that comes up in search-based algorithms, and it is defined simply as the distance of a particular node to the start. So how many edge costs did we accumulate to reach that node? And so for example, here in the case of node 1, if our root node is node 0, it would be 4. If for node 3, to node 0, it would be 4 plus 1, so that's 5. So in uniform cost search, what we do is we always go for the node with the smallest accumulated cost. So we look at which nodes can we expand, for example, on the first step 1 or 2, and we always go for the shortest possible one. So that's 2 here, because it has a lower edge cost than 1, which has 4. And this algorithm is also complete and optimal. One interesting thing to note here is that the relationship between uniform cost search and breadth-first search. So if we simplify our graph with uniform edge costs, for example, if all of the costs in that example were equal to 1, then we would simply do breadth-first search, because we would always go based on accumulated costs, which has the relationship with the depth. So we always go for the shallower nodes first. So this is one important aspect of the relationship between uniform cost search and breadth-first search. Another related algorithm is Dijkstra's algorithm, which follows the exact same expansion rules as the uniform cost search. So we always go for the node with the minimum accumulated cost. The key difference here, even though it uses the exact same rules for expansion, is that Dijkstra is, in its definition, not goal-directed. So if we have a graph, we want to find the shortest path from the initial node to all other possible nodes. In the uniform cost search, we simply follow the same procedure, but we end the search when we encounter the goal. In Dijkstra, there is no concept of the goal, so we take the whole search tree and we can have all the shortest paths from a start to all the other nodes. So this is a key difference. So as a result, because Dijkstra is operating effectively on graphs and always needs to know all of the graph connectivity, it has a higher space complexity, so we need more memory to store the graph than uniform cost search, which might actually terminate rather quickly if we find the solution in a short amount of time. So let's have a look at a detailed numerical example of Dijkstra's algorithm. And these are the same expansion rules, remember, for uniform cost search. So in Dijkstra's algorithm, we want to expand fully all the nodes on the graph, and we specify our start node, which over here is A. So we have initialized all the other edges with infinity, because we haven't been there yet, so we have infinite costs. And we only have one possible node to expand, so to generate the children of that parent, and this is A. And it has 0 cost because that's where we are in the start. So when we expand A, we get 2 new updated edges. So A is connected to B and G, which are here 10 and 5 respectively. So we can have a tree, a table where we actually put in these values in order to capture the accumulated cost from the start to a particular node. So over here, from A to B, we have an edge cost of 10. So we put 10 there, and for G, it's 5. And so the rule is we always expand the node with a minimum accumulated cost. So from 10 and 5, it's obviously 5, so the next node we go for is G. So expanding G, we can add C now to our table, and the accumulated cost will be 5 that it took to get from A to G, and the 9 that it took to get from G to C, so 14. So now this becomes a new node that has a possibility of being expanded, so a new node in our open list. So from there we go for B, because as we said, it has the lowest accumulated cost. So our options were B or C, so 10 or 14, so we went for 10. And now expanding B, we have newly generated nodes F and E, which have costs of 13 and 14 respectively. And you can just follow through by summing the numbers together. Now the node that we want to expand next is C, because it is a generated node. We haven't expanded it yet, and it has the minimal accumulated cost there, which is 10 and 1. So note that actually, when we expanded B, we found a different way of getting through C. This is an important aspect to consider. So earlier we found C through G, so 5 and 9 were 14 a total accumulated costs at C. But having expanded B, we have found a shorter route which costs only 11. So we need to update that in our table. So our parent of C has effectively changed there because we found a short way of getting to it. And this is a very important subtlety to note with the search-based algorithms. So if we want to implement them and actually find the shortest possible path in such a graph, we need to do the parent update when we find a way of getting through the same location that costs less. Right, so now that we have done that, we can move on. And actually C ends up being our new expansion node because it has the lowest cost. Then again, we can generate its children. And finally, moving on with the same logic through the example until we finish the expansion of the tree. And so there are a few aspects to note here. First, note that our expansion rule was always going for the lowest accumulated cost. So we have this table of the nodes that we could consider expanding on our open list. We always looked at the open list and the lowest accumulated cost and went for that one. And also about the parents, we need to update the parent of a node if we find a shorter way of getting through it. So if we follow these simple rules, then we do find the shortest possible paths from node A, our start, and to all the nodes in the graph and here in the table. And this is effectively showing our operation of Dijkstra's algorithm on this simple example with a few nodes. Here's a visual example as to how Dijkstra's algorithm works for a robot planning problem. So over here, if we have a start configuration, what we do is we diffuse the search space. So here the cyan crosses corresponds to nodes that were expanded, so on our closed list. And we can see how the frontier of the search space grows as it does in a uniform way, because we always expand the ones that are closest to where we started from, which makes sense. And therefore, having expanded all the nodes, we can, if we have a goal that we want to go to, we can just connect and find the shortest possible path by tracing back the parents. And this is what a mobile robot would do, for example, in a 2D environment. If we impose this grid resolution, we can apply Dijkstra's algorithm, even in this case with obstacles, hallways, mazes, and obtain the shortest possible path by following the rules of expansion. Now, having looked at the uniform cost search and Dijkstra's algorithm, a naturally emerging question is, can we do better? And the answer is yes, with informed search techniques. These algorithms benefit from what is called a heuristic. A heuristic is an essential piece of information we give to our algorithm in order to help it search for the goal. In general, a heuristic is a mathematical formulation of something that we as humans understand intuitively and instinctively. In path planning, a good heuristic is an estimate from a particular node to the goal. And we can use this value to evaluate how promising a node is for expansion on the open list. The lower the heuristic value, the lower the potential estimated cost to the goal, and the more likely we are to reach a solution sooner. Our hope is therefore that by using a good heuristic, we can focus and accelerate the search. An important condition for heuristics is called admissibility. A heuristic is said to be admissible if it never overestimates the true cost to the goal. And that's reflected here in this equation, where h is the heuristic and the star denotes the true cost. So our heuristic value that we specify is always less than or equal to the true cost, therefore it's always optimistic. Here are some examples of heuristics that we can leverage in a grid map world. We can define distance using Euclidean distance, which is the shortest line segment distance connecting 2 points. Distance can also be defined as Manhattan distance, which is the absolute sum of the coordinates of the points in Cartesian space. Are these heuristics always admissible? Well, by definition, Euclidean distance will be, because it is in fact the shortest length. For Manhattan distance, it will depend on the problem, because if our robot can navigate diagonally, then Manhattan distance will sometimes overestimate the true distance, leading to a non-admissible heuristic. And for this reason, Euclidean distance is often used as an admissible heuristic for informed search algorithms. And what kind of algorithms leverage heuristic values? Well, here we come to greedy best first search, which is an algorithm that simply expands the nodes with the lowest possible heuristic, because they're the ones that it expects to be closest to the goal. So in contrast to the previous uninformed search strategies that only looked at the accumulated costs from start to the current node, the greedy best first search only considers the node to the goal. And it's greedy because it always tries to get as close to the goal as possible in the shortest amount of time. So although this algorithm can be very fast in simple environments and makes big steps towards the goal, it is also vulnerable to getting trapped in local minima. This can happen, for example, if we have an obstacle right in front of the goal. And unless we have a sort of mechanism in escaping this local minima situation, the robot will get stuck there because it won't be able to advance due to the obstacle. The performance of the algorithm is neither complete nor optimal, and also highly dependent on the heuristic used, so we must really use it with caution in more complex environments or in situations where we really need the shortest possible path and high reliability. Let's look at an example of greedy best first search. So over here we have a physical roadmap of different cities in Romania. Here we have Bucharest, which is the capital, and some cities around. The cities are represented as nodes on the graph, and the edges correspond to the cost between the cities, so the distance. And over on the right, we can see the straight line distances between the different cities and Bucharest, which is the capital. So the straight line distances, or the Euclidean distances, we can use as a heuristic value if we want to implement a search-based planning algorithm in this environment. So one question that we could ask ourselves is, say we are in Arad over here on the top left, and we want to reach Bucharest. How would the greedy best first search algorithm do this job? Let's have a look. So we start from Arad, and we can construct a tree incrementally searching step by step until we reach our goal. So as we said, a greedy best first search will always go to the lowest heuristic value, the one that it expects to be closest to the goal. And therefore, the order of expansion here would be, we first go to Sibiu, which has 253 heuristic value compared to the others. And then along similar lines, we go to Fagaras, and then eventually we end up in Bucharest. And again, these heuristic values are based on the Euclidean distance that we got from this table here. So this is the information that we give to our algorithm that we didn't actually have when we only considered uninformed search strategies before. And following this order of expansion with the greedy strategy, we arrive in Bucharest with a total cost of 450. However, looking at the graph, we can observe that there is actually a shorter route. So if we go this way, in fact, we will only accumulate a cost of 418. But our algorithm was not able to find this path first because of the greedy nature of its expansion. So this is a situation where the greedy best first search algorithm does actually produce a solution, but it is not the optimal, not the one with the shortest total cost. So, can we somehow get the best out of both worlds? We looked at uninformed search strategies, which only consider the accumulated cost and implement simple rules for expanding nodes. And then we looked at this greedy best first search algorithm, which quickly advances towards the goal, but has many drawbacks in terms of optimality and completeness. So just to recap, the uniform cost search, for example, an uninformed strategy only considered the accumulated cost here when it considered the total cost of potential nodes for expansion next. So these are our nodes on the open list here. And we always looked at cost in terms of cost from the start. And what our greedy best first search strategy did is just consider the cost on the other end. So an estimate of how much would it cost to actually reach the goal from where we currently are. So it only considered the heuristic cost. Can we get the best out of both worlds? And this is what the A-Star algorithm, which is a very commonly used algorithm for planning applications, actually does. So it simply sums up the accumulated cost and the heuristic value in order to formulate the total cost. So when it looks to see which nodes on the graph that are on the open list it will expand next, it formulates their total cost based on both accumulated cost and the heuristics that we get as additional information for our problem. So how does this look? Here is a visual example where if we're considering this node n and we have a starting node here on the left and a goal node here on the right, then we want to sum up an entire path. And say this is the best possible estimate that we can have of the total path length. So we already know the path that we took to get to that node because we have expanded the tree from the start. And we can guess the heuristic, well estimated, based on, for example, the straight line distance. So this is the A-Star algorithm and the fundamental way in which it uses and puts together all the concepts that we developed so far. So in order for it to be optimal and complete, A-Star needs to have an admissible heuristic. And this is where the admissibility condition is absolutely fundamental. We need to make sure how we specify the heuristic value in order to get these properties of our algorithm. Otherwise, say if we overestimate some of the paths in comparison to the true cost, the algorithm might not consider that a promising search direction, even though in reality it may be the best possible path that we can get. And so for optimality and completeness, it's crucial that our heuristic value is admissible. We can also use overestimates of the heuristics. The search will be faster, but it is suboptimal. So a natural question that we asked ourselves then is there a way of getting the best possible or the optimal heuristic which reflects the true cost from a node to the goal? And this is a question that we can think about now and we come back to later on in this lecture. And first, let's have a flowchart visualization of how the A-Star algorithm operates, so the flow of data. So if we start here and O is our open list, we have to basically pick the next best node according to the heuristic value. And then we take that node, we expand it, and we check, did we reach the goal? And if we didn't reach it, then we generate all the children of that particular node, so the node has been expanded. We add them to the open list as candidates for the next expansion, and we repeat the process. So this is essentially keeping a collection of nodes that have been generated, not expanded, checking their total estimated cost, picking the one with the lowest, and keep doing that until we reach the goal or exhaustively check all the nodes on our graph. An important point to make here is what's happening here is that if we actually reach a node in a different way, but with a lower cost, then we need to update its parent. And this is something that we have seen earlier with the uninformed search example with Dijkstra's algorithm. It's a fundamental step to make sure that we're actually always taking the shortest possible path. So moving on to a numerical example of the A-Star algorithm in action on a graph. So over here we can see the distances between some nodes on a grid. As before, each node has a letter to identify it, and we have some edge costs here, 1.5, 2, 3, etc. So we also have heuristic values associated with each of these nodes. Now what we're trying to do is we're trying to move from the start node S to the goal node G. And so we'll have a look step by step as to how this is done using the information that we have here with the A-Star algorithm. So at the beginning we start over here at S, and we have heuristic value of 4 that we get from the table, and the only node that we can expand there is actually S. So we have now generated new nodes C and D because of their connectivity to S. And we can put the edge lengths as well as the heuristics. So for C, for example, we have one edge connecting S and C, that's 1.5. So that's our G of n, our accumulated cost to reach that node. And then we have our heuristic cost, H of n, which is 2 that we can get over here from the table. So the total cost, that F of n that we use to estimate how promising this node is simply the sum of them, so 3.5. And we can do exactly the same thing for node D. So we add 2, the accumulated cost, and then we must also add the heuristic 3.1, so we get 5.1 there. So this is how we can compute the total costs here of the nodes that have just been added to the open list. And then we look at our open list, so thus currently C and D having expanded S, and we have the one with the lowest is node C. So then we repeat the procedure and add the children of C. So that would be A, B, and E. So there we didn't touch D yet, but we have 3 new nodes on our open list there, whereby we get the total cost by summing up the cost to reach them. So for example, for A, 1.5 plus 1, and the heuristic, that's 3.1. And then we sum up those values, and that's our total cost for each of the new nodes. And we can repeat this process again. So now we have new nodes added. The only difference is that we took 2 steps, so we're deeper in the tree now. But the main logic is the same. So now D is actually our new one with the total lowest cost. So we go for that one, we expand it, and then we can add E over here. And we can repeat this process step by step until we have actually reached G. And the algorithm finds that the cheapest path from S to G is actually S, C, B, G, and hopefully by also looking at the graph, and using our human skills, we can confirm that this is indeed correct. And over here, we followed exactly the same logic as Dijkstra's algorithm. So looking at the open list, expanding a node and repeating that until we reach the goal, or expanded all the nodes on the graph. But the key difference is here that we also added this heuristic value, which is a measure of how promising a node is in the future as well. So this way, we combine the benefits of the path that we have just traveled and the path that we have yet to take, the prediction. So here's a comparison now that we talked about Dijkstra of how A-Star and Dijkstra performance behave. So in an environment without an obstacle, we can see clearly the benefits of doing A-Star. Because A-Star will be biased and is directional, there is something about the goal that's actually pulling it there. Whereas Dijkstra will expand uniformly, so it only cares about the distance from the center and does not care about any distances, even estimates to the goal. With an obstacle, we can see the same type of behavior. So Dijkstra expands uniformly and kind of diffuses around the obstacle, even very far away from the goal. Whereas in the case of A-Star, we can find that we can expand much less nodes, so we can reach the solution faster because we're weighting less these nodes that are, on the other hand, far away from the goal. And we can confirm here that A-Star actually is able to go around the obstacle in a very short way, finding the optimal path. So because of its directionality, it wouldn't go around or diffuse. It does actually find a very close path in this sharp environment, so it takes a very sharp turn in order for the robot to reach the goal. And finally, an animation, just to consolidate these ideas of A-Star and Dijkstra in the same environment working together. And here, again, we see Dijkstra spreading uniformly, whereas A-Star is much more directional due to the heuristic, which drives it faster towards the goal. And so if we have these types of problems, A-Star, and we care about efficiency quite a lot, then A-Star is the one that offers these benefits by the use of the heuristic value. And it's just important that the way in which we specify the heuristic, and if we care about optimality, then we do need an admissible heuristic. And next we come to weighted A-Star, which thinks about the relationship between this accumulated cost and the heuristic values. So, is there a way of making the search more greedy at the beginning, for example? Or can we somehow tune the weights of this accumulated cost versus the heuristic cost? Can we say that the heuristic is more important so that we have greater attraction towards the goal, so that it behaves in a more greedy way? Or can we somehow gradually tune the weights of these two things so that our search exhibits actually some kind of adaptive behavior based on where we are in the planning mission? Weighted A-Star does just that. So it is a linear combination of the accumulated costs and the heuristic value. And by using a static weighting, we can weight the heuristic more so that the search becomes more greedy and drives us closer, faster towards the goal. On the other hand, a dynamic weighted A-Star is one where we actually have a variable that depends on the depth of the search. And the closer we get to the goal, the less we weigh our heuristics. The intuition behind that is that at the beginning, we want to take large steps towards the goal because we expect to be far away, for example. So weighting the heuristic more will make us act in a more greedy way, take larger steps. And then later on in the mission, thanks to this weight that decays over time, we actually start weighing relatively more the accumulated costs, and we can tune the search because we have already traveled a lot and now we want to weight the accumulated cost more when we reach the goal. So this is a way of biasing these two elements. And in practice, what we could also do is say that, for example, beyond a particular depth, we want to remove the weighting on the heuristic and we want to quickly go to the conventional A-star algorithm. This is something that is a subject of a significant area of research. How can we generate effective heuristics and also weight them appropriately in our algorithms? So here's a visual illustration of how this all works. So in the case of A-star, say we have a start node here, a goal on the opposite end, and an obstacle in between. So what the conventional A-star would do is try to diffuse towards the goal. So it is much more directional, remember, than Dijkstra that considers the area around the start. But it would waste significant time exploring this area that's actually in between the start and the obstacle. This is a situation where the weighted A-star could actually be very useful. And so, for example, with a static weighting, if we say we want to weight the heuristic more, then we can take bigger steps. We say that the goal attraction is very high relative to the cost to get to the particular node. And so we don't have to waste the computational resources on expanding this part of the search space because we can take big strides. What a dynamic weighted A-star algorithm would do is combine this type of behavior. So at the beginning it behaves more like a static weighted A-star, and then over time, as we continue on the search, the weight would take an effect and it would behave more like a conventional A-star. And for example, one of the potential reasons for doing this could be in order to get a more optimal path to the solution that actually behaves more around the corner, so takes a shorter path and circumvents this extra distance that we needed to travel here in order to get around the obstacle. So it really depends on how much resources do we have, especially how fast do we want our solution and how close we want our solution to be to the optimal. Because by weighting the heuristic more, we can get highly suboptimal solutions because our heuristic loses those nice properties of admissibility. And finally, on the topic of the heuristic, one thing that we might consider is, if we start thinking about it, is that an optimal heuristic could be actually generated by Dijkstra's algorithm. Remember, Dijkstra's algorithm is an optimal algorithm, an uninformed search strategy. So if we run it from the goal to the start, then we should be able to find the reverse cost that we actually need for our A-star heuristics. Could we actually do that so that we can get the optimal heuristic? Well, the main disadvantage of this is that it's not practically feasible, because if we ran Dijkstra's algorithm, then we have already solved our problem. But this could be very useful in a different type of problem, which we're going to discuss next. And with that, we come to the most challenging, but also the most practical type of scenario where we can use search-based algorithms, which is in dynamic environments. And we'll have a look at how we can put together everything we learned so far and apply it in this type of problem. So dynamic environments are ones which have moving obstacles whose positions change over time. This could be, for example, this urban scene where we can see pedestrians as well as other robots. And a naive strategy here is to apply A-star continually, replanning from time to time. In this case, this heuristic that we mentioned, generated by Dijkstra's algorithm, would actually be useful, because we can only compute it once and keep reapplying it every time we want to run A-star and the situation in the environment changes. it can be shown that this heuristic is still admissible even in these types of dynamic environments. Here's a flowchart of what the A-Star Replanner would look like. So we first generate the path in a known map using the conventional A-Star, or weighted A-Star if we want. And then when the robot moves, we need to check whether there has been a discrepancy in the environment. So if the obstacles have changed. If so, we need to update the map and rerun everything from scratch. This preserves the nice optimality properties of A-Star, but as we can already see, it's very inefficient because it requires rerunning A-Star many times. And this could be especially disadvantageous in large environments, where we have a large problem space to explore. The final algorithm that we look at in this lecture addresses this issue. It's called D-Star Lite. D-Star Lite is based on an algorithm called D-Star, which stands for Dynamic A-Star. D-Star Lite is the one that we covered here because it's a simplified version and also preserves a lot of the nice properties of the original algorithm. And the main motivation for the design of this algorithm is its applicability in dynamic or partially known environments. So what we want to do is avoid this constant replanning that we would need to do with the conventional A-Star. D-Star Lite addresses these problems by replanning online. So it has a formulation of the graph, and its key idea is that it allows the edge cost to change during the search so that we can effectively repair the path as we encounter new obstacles. This is much smarter because we do incremental, small changes to our path rather than recomputing everything, as in the previous slide. So we're just going to cover D-Star Lite on a conceptual level here so that we can understand how it works. And you can find the full implementations in the further reading. So unlike A-Star, D-Star Lite actually plans a path from a goal to the start. And the reason for doing this is because this incremental path repair is easier and more efficient if we do it the other way around. So the search direction is basically the reverse of what we considered so far in this lecture. And then how are these edge costs addressed? So D-Star keeps track of 2 scores for each node. We have the traditional G-score, which is the accumulated cost to reach that node. However, this time we define the accumulated cost from the goal because this is where we started from. But the concept is essentially the same. And the new part is this RHS score, which is a one-step look ahead. An RHS score is simply the sum of the G-score to reach the predecessor or the parent of a particular node, plus that small incremental cost to reach from the parent to the child. So we basically decompose the G-score into the G-score of the previous node and the one further ahead. And we constantly store these 2 types of score for each node. This is the basic idea and the enlightenment of the D-Star algorithm. So by looking at the RHS store, we can perform very incremental changes to this one-step cost. For example, if we notice that we saw an obstacle in between the parent node and the current node, which is a child, therefore we need to update the cost to infinity because we can't move there. So we will constantly update this RHS score. This way, by comparing the RHS score to the G-score, we can detect inconsistencies and replan incrementally as necessary. The total estimated cost in this algorithm will be given by the minimum of these 2 scores, plus a heuristic value that is, again, in the reverse direction from the current node to the start. So conceptually, the idea of Dykstra is very similar to A-Star, except this time we introduce an additional bookkeeping so that we can detect changes, fix paths. And everything is done the other way around because our search takes place from the goal to the start rather than from the start to the goal. So without going into too much numerical examples, let's just have a visualization of what Dykstra Lite looks like if we want to implement it in a grid world. So in red here we have the robot, and let's say we're trying to get exactly to the opposite side of the map on the diagonal. And here in the orange, yellow, and the green we can see an initial path that was generated without knowledge of whether any obstacles are moving. And then as the robot moves, say it has advanced a little bit and suddenly there's an obstacle, it's in its way, so it has detected something. And in this type of situation, what Dykstra Lite will do is fix the solution. So now rather than going through the obstacle as we would do with A-Star without replanning, the robot can take a way around and fix its path, keeping the rest of the nodes on the path the same, just fixing that small patch that was found to have an obstacle in it. So this allows us to do something that we couldn't do with the A-Star Planner in dynamic environments, and is much more efficient than the A-Star Replanner, which keeps recomputing the path in an inefficient way. So with this we come slowly to the end of the lecture and the final summary. So we first overview search-based methods, the key inputs we need for our algorithms and how to implement them, giving a very conceptual high-level scheme. Then we moved on to look at uninformed search strategies. And then we addressed some of the shortcomings of uninformed search by introducing heuristics, especially focusing on the A-Star algorithm and how it leverages heuristic value and accumulated costs in order to find the best possible paths. And finally, we discussed briefly how we can implement these search methods in dynamic environments and mentioned the A-Star Planner and Dykstra Lite here. Now for further reading, again there's plenty of resources that you might consult. Especially recommended are ones that have animations or pseudocode that you can play around with and see how these search-based methods actually work in practice and in different types of environments. Thank you for your attention.